Alright, this video has the solutions to your semester exam review. Starting with number 1. Code section below is indicated to swap the values. It seems like the College Board is obsessed with this particular little thing here where we swap the values of two things. So you need to put first into temp. Alright, so if you had your variables here, little places where what's being stored in which variable. So I'm going to put first into temp. So now that's first. This is still first. This is second. And then I'm going to put second into first. So I'm going to move that over to here. So that's second now. And then the reason we have temp is so that we could have stored, so we didn't write over that value. So I need to put temp into second. Is the missing bit. Seen that a lot of times. Number 2, consider the following program which uses the variables start, end, and current. Okay, so start is 1, end is 20, and current is 3. So I'm going to do the same thing again. Here's my start, end, and current. Start right now is 1, end is 20, current is 3. So I'm going to put current into start, and I'm going to make current equal to current plus 1. And then I'm going to display start and display current. So it's going to be 3 and 4. That's which ways to see. Let me write these big on here, so if you're just scrubbing through the video, you can check your answers. All right. Ticket prices at a movie theater are given below. $12. Is that how much movies cost these days? Yikes. Children are $9, and seniors are $9 also, and $5 extra for 3D. Programmer is writing an algorithm to set the value of ticket price based on the information in the table. Programmer uses the integer value age, and the Boolean value is 3D true when the movie's 3D. Okay, so which of these is going to make the ticket price right? So if the age is less than or equal to 12 or greater than or equal to 60, then the ticket price is 90. So this is not going to do it because we need to check their age, and then also like in the same block of code, this isn't going to give. So in other words, if this was a kid and they were watching a 3D movie, it would make them pay $17 because it would set it to this and then it would reset it to this. So that's no good. Yeah, that's no good. Is that the same thing? How is this different? I feel like this is the exact same answer. Ticket price. Oh, else. They didn't do that. Is 3D, I see. But that still doesn't work. Here we go. I think so we're setting the ticket price. I think I like this one. Let's see. Setting the ticket price to 12. If they're less than or equal to 12 or greater than or equal to 60, then we're going to reset it to 9. And then if 3D is true, we're going to add 5 to the ticket price. I think that works. I'm just going to make sure that this one is not good. Yeah, this one's not good because it's not checking the is 3D condition, right? It's not else. So this would make everybody's ticket price go up if they were not in this age range. So C, that's the right answer. All right, number 4. Which of the following best characterizes a high-level programming language? High-level means like very abstract, like up toward human language kind of direction. Language comprised entirely of hardware logic gates. Boo. That is low level. A language in which each instruction corresponds directly to an instruction in a computer's machine code. So that's very low level. If you have to say everything like at the machine code level, that's where a lot of detail, not high level. Language that is easy for a computer to interpret but difficult for humans, that's the wrong way around. And the D, a language that uses multiple abstractions to manage complexity. That's what we want. That is a feature of a high-level language. So 3 was C, 4 is D. And Number 5. Which of the following best describes one of the benefits of using an iterative and incremental process of program development? It allows programmers to implement algorithmic solutions to otherwise unsolvable problems. That's kind of a weird answer that you probably suspect is not true. Allowing programmers to implement algorithmic solutions to otherwise unsolvable problems. That's just a weird thing to say. I don't know what to say about that, but it's not right. It eliminates the need for programmers to test completed programs. That's nothing eliminates the need for programmers to test completed programs. It enables programmers to create programs that use the lowest level abstractions available. I don't even understand what that means. Low-level abstractions? What does that even mean? It helps programmers identify errors as components are added to a working program. Oh yeah. So iterative and incremental means like you're going through and like adding and improving and going through that process. In other words, not trying to write your program like from line 1 all the way through as the first step of your process. Number 6. The procedure draw circle XYR can be used to draw a circle on a coordinate grid. Circle is centered at XY and has a radius of R. The procedure will be used to draw the following figure right here. So which of the following segments is going to do this? So X position 3 and 6. Let's see, where's 3, 6? So that's not a bad start. And then repeat 3 times, draw a circle of radius 2. So the first time that one's going to be in the right spot. And then I'm going to increase the X position by 2 and the Y position by 2. That would make the second circle up here. So I think I need to go over 2 and then down 2. So if that was a minus there, that would be good. So this is looking good here based on what I figured out from that one. So just going to check these other 7, 2. So that would be starting here. And then this is the add 2 to each coordinate. That would move me over to here. That's no good. And this is add 2 to the X, and so that moves me down here. So yeah, this is the right one. Number 7. Consider these 2 programs here. Let's see what they do. So I'm going to store 1 in I, repeat until I is greater than 10, display I, and then kick it up 1. And then here, store 1 into I, repeat until I is greater than 10. Okay, so we're just reversing the values of these. So this one adds 1 first and then does display I, and this one displays it and then adds 1. So they don't do identical values. This one is going to display, so this one's going to display 1 through 10, and this one, the first time it displays, it already added 1 to it. So this is going to do 2 through 10. Nope, 2 through 11, because read until I is greater than 10, so when I is 10, it will repeat that last time, make it 11, so 2 through 11. Program A and B display the same values in different orders. Program A and B display the same number of values, but the values differ. Program A and B display a different number of values. So C is the correct answer. Right? Because both of them, they're not going to display a different number of values because the incrementing I by 1 is happening inside the block. It's in a different place, and that's changing what gets displayed, but it doesn't change how many times it's going to go through until it gets to that condition. Number 8, an application program interface provides a procedure max, which returns the greater of its 2 integer arguments. So you put in 2 numbers and it returns the bigger one. A programmer would like to find the greatest of 3 integers. Which of the following expressions will produce the desired result in every case? So, I mean, if you find the max of... Oh, wait a minute, is this right? Max, yeah, that's right. So this finds the biggest one of A and B, and then this finds the biggest one of whichever biggest one here in C, so that finds the biggest of the 3. All these ones, like if you're adding and subtracting things, we're just trying to find the biggest one. So all this addition and subtraction I don't know, it seems like it can't, none of this could possibly be right. Just looking for the biggest one. So find the biggest one, and then compare that to the other one, find the biggest of those. And that'll do it. Oh, it's a robot. Okay, so the following question uses a robot in a grid of squares. The robot is represented by a triangle, which is initially here, facing right, and we got two procedures. We want to move it to this gray square right there. So procedure move x times, repeat x times, move forward, and procedure right x times, and I'm going to rotate right that many times. Okay, so that's what I've got. I've got move forward and rotate right. So move x times 2, rotate right one time. Well, rotating right is going to turn me that way, so that's no good. Here I go 2 units this way. I rotate right 3 times, so that turns me this way, and then this way, and then this way. So that gets me pointed the right way. I think this is our winner. Since I can't rotate left, I have to rotate right 3 times instead. Let's just make sure these other ones are wrong. Move x times 3, and then right, that's not right because we only want to go forward 2. Same thing here. So B is the right answer there. Number 10, students creating a procedure to determine whether the weather, haha, it's kind of funny, for a particular month was considered very hot. The procedure takes as input a list containing daily high temperatures for a particular month. The procedure is intended to return true if the daily high temperature was at least 90 for a majority of days in the month, and then false otherwise. All right. This is one of these missing code problems. So let's see what it's doing here. Is hot, and then we got my list of temperatures. Total 0, counter 0. For each temperature in the list, so it's going to cycle through the list. If temperature is greater than or equal to 90, then I'm going to add 1 to the counter. And then I'm going to add 1 to the total regardless. So this is counting how many days, and this is counting how many days that the temperature is greater than or equal to 90. Okay, and then what I want to return is counter. That's the number. I'm just going to write this here. So counter is number of hot days, and total is total days. So I want the majority of days to be over that. So that means that this number divided by this number, so counter divided by this, if that's greater than 0.5, right? And then like algebra wise, they don't have this as an option, so they multiply this over to the other side. You know how to do algebra 1, right? I'm just multiplying that to the other side. So counter greater than, that's this one, B. All right. Which of the following is an underlying assumption that is made when Moore's law? Moore's law is that the number of transistors can like doubles every couple of years. Remember that? As computer hardware improves, the algorithms used in programs will become more efficient. That's not really true. The algorithms are independent of the hardware. We can run those algorithms faster, but the algorithms aren't going to improve just because the hardware is improving. As computer hardware improves, developers will become more skilled at writing code. Probably generally true, because computers have been around, programmers have been around longer, learning more stuff, but that's not what Moore's law is about. As computer hardware improves, future computers will be able to run faster than current computers. Oh yeah. As computer hardware improves, the number of cybersecurity concerns will increase. Also probably true, but that's not what Moore's law is about. A text editing application uses binary sequences to represent each of 200 different characters. What's the minimum number of bits needed to assign? Okay, so how many binary bits do you need to get 200 things? If you have one bit, you got one bit's going to give you two possibilities because that's 2 to the first power, and then 2 squared, you have 2 bits, you got 4 possibilities. So it's just like which power of 2 is going to be the first one that's bigger than that, and that's 2 to the 8th is 256. So you need 8 bits to cover that. Number 13, student wrote the following code. Cool. For a guessing game. Okay, secret number, picking a random number between 1 and 100. I'm going to make the variable win as false. So we're going to repeat this until win, or in other words, until it's true. Okay, so display guess a number, we're going to take an input from them. If their guess is the secret number, then we're going to display you got it right. And else, if their guess is greater than the secret number, then your guess is too high, else your guess is too low. And then we're just going to keep doing that. Alright, so I think while debugging the code, student realizes that the loop never terminates. It just keeps doing this. And that's because they're never making win. If we're doing this repeat until win, then at some point you have to make win true. So I think that would be here, right? When they display you got it right, then you'd also have to make win true. So where would win true be inserted? Between 9 and 10. Right, we need it right in there. Right, because that's when they got it right. Number 14, color is often represented by a 6-digit hexadecimal number. This is the same as the RGB stuff that you guys were doing. If you have like these numbers, a 6-digit hex number is can take, if you've got this like 0 to 255, 0 to 255, 0 to 255. I think you saw this in the notes, but this can be a 2-digit hex, right? Because 2 digits of hex can go from 0 to 255. So a 6-digit hexadecimal number can give us these two, and then these two. Common way of doing it, for sure. From left to right, the first 2 digits represent the amount of red, that's the amount of red, amount of green, and then the amount of blue. Which of the following hexadecimal numbers represent the color?
The Cyber Club meeting that was scheduled for today has been postponed
until
January. The Cyber Club meeting that was scheduled for today has been postponed until January.
And that announcement in the middle of computer science stuff. Alright, so from left to right, first 2 digits represent this is the amount of red, the amount of green, amount of blue, right? So RGB, just like we're used to. Which of the following hexadecimal numbers represents the color with the greatest amount of blue in it? So that would mean that the biggest number here. So I'm looking at, that's the amount of blue. So which one of these is the greatest hex number? Well, it's the one with the biggest number in this place, so it's this one. Just for practice, A1 in hex, that's A is like the 10, so that's 10 16s plus 1 1. That's 161. 9 9 is 9 16s and 9 1s, which is, oh boy, math, 90, 100, 100 and I think. You can use a calculator, of course. This is B is 11, so that's 11 16s and no 1s. That is 176. And that's 0. So So that's the biggest one. But you didn't actually have to do that, because if you just look at the front digit, like just like if you were looking at a bunch of decimal numbers, you said like which number is the biggest. You're not going to look at any number. You're going to look at this first, right? If the 9's bigger than all the other ones, well, that's the biggest number. It doesn't matter what comes after. So B is the biggest. So there you go. Number 15. Some logic gates here. Each gate takes 2 inputs and produces a single output. And which one of the following inputs will the circuit have an output of false? Alright, well, let's just try them. There's only 4. So if I do true and false, that's going to give me a false when I put those two together, right? Because and they have to both be true. And then false, false, that gives me a false, right? False or false. And then so I have a false and a false going to this OR. That gives me an output of false. So there it is, A. Let's just check the other ones. If either one of these inputs here is true, that's going to give me a true here, because this is an OR gate. So true, true, that's going to give me a true on this side, and so that's not going to work for trying to get a false out of it. And here, false, false, that's good. True, true, so that's no good, because that's going to give me a true on this side, and that's an OR. And then false, 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 true, that still gives me a true on this side, so A is the answer. Number 16, musicians creating a song using audio samples. Which of the following actions will minimize the risk of a copyright violation when creating sample-based music? Using samples found on popular music streaming sites. No, we don't know. You don't know about what's going on with the Creative Commons and all that. Using samples found on peer-to-peer networks. Oh boy, nope. No good, right? Just because it's on a peer-to-peer network, that does not mean it's fair game for sampling. Using samples from non-digital sound sources, vinyl records. Well, vinyl records and tapes still have the same copyright kind of issues, so that doesn't matter. Using samples published with a no rights reserved Creative Commons license. All right. A computer program performs the operation 2 divided by 3 and represents the result as this. Of course, the real 2 divided by 3 has 6's that go on forever. Which of the following best explains this result? An overflow error occurred. Well, it wouldn't if there was an error, it wouldn't display this. The precision of the result is limited due to the constraints of using a floating point representation. So floating point's only going to give you so many total decimals that you can have, so that seems like that's going to be right. The program attempted to execute the operation with the arguments in reverse order. Well, 3 divided by 2 is 1.5, so that's bad math. And last choice, the program attempted to represent a floating point number as an integer. That's not an integer, so no. All right. For 18, a flowchart is a way to visually represent an algorithm. Flowchart below is used by an apartment rental website to set the variable include to true for apartments that meet certain criteria. And then this is just the explanation of the different parts of a flowchart. You know about that. So let's see. Start. If floor is greater than 10, then if that's false, so if their floor is not greater, if number of floors, I guess, is not greater than 10, bedrooms is 3, false, then we're not going to include it. So if we have more than 10 floors, if we have fewer than 10 floors, and we don't have 3 bedrooms, then we're not going to include it. If we do have greater than whatever this variable means, if floor is greater than 10, then we're going to include it, no matter what. If the floor is not greater than 10, but it has exactly 3 bedrooms, then we are going to include it. Right, so it looks like we if the floor number is greater than 10, then we're automatically going to include it, whether there's however many bedrooms there are. But if that's false and there's exactly 3 bedrooms, then we're going to include it also. Okay, so let's see if we can figure out which one of these is the same. Floor is greater than 10 or bedrooms equals 3. I think that might do it, right? The floor is greater than 10, but if that's not true, then that happens. Yeah, so I think that this is it. Floor is greater than 10 and bedrooms is greater than 3. That would get us there, but we don't need both of these to be true, because if floor is not greater than 10, you can still get to the include. So that's not it. If floor is less than or equal to 10, or bedrooms, no, that's not right, because of the floor being greater than 10 is the desirable thing, so those are not right. All right. Number 19. Computer uses 4 bits to represent non-negative integers. So 4 bits is going to get us from 0 to 15. Right? If you fill them all up, that's 15. Which of the following statements describes a possible result when the program uses this number representation? The operation 4 plus 8 will result in an overflow error. No, 4 plus 8 is okay. That's in our range. So that's not true. The operation 6 plus 10 will result in an overflow error. Yes, it's too big. 12 plus 3 will result in an overflow error. Just 2. 17 is too big. A snack bar has a frequent customer program in which every 10th purchase is free. Customers are enrolled in the program when they make their first purchase. A programmer is writing a program to implement the frequent customer program. In one code segment, cost is set to 0 for every 10th purchase by a given customer. Okay. The programmer will use the procedure getCount customer ID, which returns the total number of purchases a customer has made since enrolling in the frequent customer program. Okay, I think I understand this. When you do getCount, that's going to tell you like the number of purchases they've made, and cost is going to be set to 0 for every 10th purchase. All right, so count. So I'm going to get, this is going to get how many purchases they've made, right? And put it into the variable count. So if count divided by 10 is equal to 0, then the cost is, well, I don't need count. The only way count divided by 10 is going to be equal to 0 is if count is 0. So that's not right. You need to do some kind of like mod thing, right? If not, that's not right. So I need the remainder, right? The count mod 10 is 0, then we want to set the cost to 0. If not count mod 10, so this code here, you don't want this code if you're the retailer. This is going to set cost to 0 whenever, like for every single purchase except the ones that are multiples of 10. Right. Number 21, a NAND gate is a type of logic gate that produces an output of false only when both of its 2 inputs are true. Okay, so the only way, so true and true, if you put it into a NAND gate, gives you false. That's for not and. And that's exactly what it does. It's not and. Which one of the following Boolean expressions correctly models a NAND gate? So you can mess around with these different ones, but this is the correct one. It does the exact opposite of an AND gate. So it takes these two, only if they're true does it return false. Oh, wait a minute. Well, let me check this. Both inputs are true, otherwise It's an output of true. Yes, this is correct. So if you're wondering, I think this is the other maybe possibly tempting answer, but not P and not Q is going to do oh, no, I'm second guessing myself. Hold on, let me just make sure that this is true. I'm going to make a little chart here. This is called a truth table. So I'm going to make, let's see, for P and Q, for my values of P and Q, there's 4 possibilities. It could be true, 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 false, false, true, false, false. So the P NAND Q, not AND Q, they told us that that makes false only when both inputs are true, and then true for all the other ones. And then I think that it's this, but I'm just going to make sure. So not, so let's just do P and Q. P and Q. Sorry, I'm crashing into my little picture here. P and Q is true, false, 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 and then not P and Q. Yeah, that's going to flip those. So not P and Q is correct. All right, just needed to double check, make sure that it wasn't that one. 22. An online retailer uses an algorithm to sort a list of n items by price. Tables below shows the appropriate number of steps the algorithm takes to sort the lists of different sizes. So as this increases by tens, this is going up by squares. So this is something that we'd say this is running in polynomial time, because this is like 1, 4, 9, 16, 25, and so on. This is like this number squared. So based on the values in the table, which of the following best characterizes the algorithm? First of all, it ain't good because it's increasing like as a power of 2 compared to the number of items. Does it run in reasonable time? No. The algorithm runs, but not in reasonable time. The algorithm attempts to solve an undecidable problem. I don't know what that answer is doing there. I mean, this is, you know, it's doing it in that many steps, so definitely not an undecidable problem. The algorithm attempts to find an appropriate solution whenever it fails to find an exact solution. Well, I don't know what that has to do with this. Nothing. I mean, it's doing it, right? It's finding the solution. It's just taking an increasingly long time. So we say if you feel like this is too fuzzy, reasonable, not reasonable, an algorithm, you want it to either get more efficient or like maintain like a kind of linear scale with the number of inputs. If it blows up like this, that is not good for large data sets. All right. Oh, there's no number on this one. Uh-oh. So I guess this one is 22 and a half, because the next one's 23. Sorry about that. 2 code segments below are each intended to display the average number of the numbers in the list numList. Okay, here's program 1. Set the sum equal to 0. For each number in the numList, we're going to add it to the sum, and then average. I think that we don't want to average them until we're done, right? That needs to be outside. So this looks better, because this is going to keep messing with the average. We're not going to get the right average here because it's going to keep changing every time. That's not how you average numbers. Which of the following best describes the 2 code segments? Code segment 1 displays the correct average. No. 2 displays the correct, 1 does not. Both code segments display the correct average. So just B is going to do it right. You can try with a list of numbers and see if it, like averaging, doing this every time is going to get you the right average. It is not. Number 23. Grid below contains a robot represented as a triangle initially facing up. Robot can move into a white or gray square, but cannot move into the black region. Code segment below uses the procedure goal reached, which evaluates to true if the robot is in the gray square and evaluates to false otherwise. So repeat until goal reached, and we want to see which one's going to get it to the gray square. Okay, so if can move right, then rotate right, and then move forward. And then it just keeps doing that until the goal's reached. Okay, so let's see. If I can move right, no. Then rotate right, otherwise move forward. Okay. If I can move right, nope. So move forward. If I can move right, nope. So move forward. If I can move right, then rotate right, yes. So now I'm going to be pointing this way. And then I move forward, can't move right, so forward, forward. Can't move right, so forward again, and then turn. So this basically does like, if you can go right, then it's going to turn you to the right, and if you can't, you just move forward. So because this is all right turns to get into here, this is going to work. That's going to get us there. Let's just check the other ones real quick. So if can move right, then rotate right and move forward. Let's see, that seems like it might have a chance too. So let's see. If can move right, no. Oh, because there's no other thing, right? So if I can't move right, which I can't here, then there's nothing else. It's just going to get stuck in that loop forever, because goal's never going to get reached. If can move forward, and otherwise rotate right. So move forward, move forward, move forward. I can't move forward now. Oh, this is going to keep rotating me right every time. Sorry, that's not inside the if. So that's going to move forward and then rotate right. Can I move forward? No. So rotate right. Can I move forward? Yes. So that's going to go down to here. And that's just going to bounce back and forth between these two, if you follow that. Stuck in that loop forever. If can move forward and rotate right. So this is going to be another similar issue to this. If you can't move forward, then there's no else, and then you're going to get stuck forever doing nothing. So A is the correct answer. Number 24, student wants to create an algorithm that can determine, given any program and program input, whether or not the program will go into an infinite loop for that input. Okay, so I don't know how much you know about the history of computer science and who Alan Turing was and all that kind of thing, but this is a famous, very famous problem. This is the halting problem. And I can't remember if in our notes if that was ever in like when you were talking about the lengths of the run times of algorithms, if this was mentioned or not. I think probably it was. So anyway, it's well known in computer science that the halting problem is not solvable. Like there is no code that can determine if all programs either terminate or not. The problem the student is attempting to solve is there you go, it's an undecidable problem. Which of the following is true? It is possible to create an algorithm, nope, that will solve the problem for all programs and inputs, but the algorithm can only be implemented no, that's not true. It's not possible to make the algorithm. It is possible to create an algorithm, no, it's undecidable, so you can't do it. It is possible to create an algorithm, nope. It is not possible. Like, that's what it means for it to be undecidable, that it's not possible to make that algorithm. Now, that doesn't mean that it's never possible to tell if a program is going to halt or not for all inputs. It just means that it's not possible to determine that for all programs, to make a program that will determine it for all programs and their inputs. I think I'm going to stop this video there, and I'll finish the rest of these in a second video, which I think we'll be a little bit shorter than this one, because I got through number 24.